There are 10 amazing facts about quantum artificial intelligence. Greetings from the future. This is a universe in which the seemingly impossible becomes possible and science fiction transforms into reality. In this groundbreaking episode, we explore the intriguing topic of quantum artificial intelligence, AI, a cutting-edge field that holds the potential to fundamentally alter our knowledge of the cosmos and drastically alter our existence in ways we can only begin to comprehend. We're going to explore 10 astounding truths regarding quantum artificial intelligence today. Imagine resolving intricate issues in a matter of seconds that would have taken millennia for the most potent supercomputers. Stay tuned as we continue to uncover more amazing secrets about quantum artificial intelligence, such as the ability to transfer data and decipher the workings of the human brain. This is a voyage that you will not wish to miss. Number 10. The quantum world is lumpy. The quantum universe and shoes are very similar. It's not possible to simply walk into a store and choose footwear that perfectly fits your feet. Instead, you must choose from pairs that come in predetermined sizes. The realm of subatoms is comparable. Albert Einstein received the Nobel Prize for demonstrating the quantization of energy. We use the moniker quantum physics because energy only exists in multiples of the same quanta. Similarly, shoes are only available in half-size increments. The Planck constant, so called in honor of Max Planck, the founding father of quantum physics, is the quanta in question. He was attempting to resolve the conundrum regarding our comprehension of hot objects, such as the sun. We observe the energy these objects release, yet our best hypotheses fail to explain it. He successfully reconciled theory and experiment by proposing the quantization of energy. Number 9. Something can be both wave and particle. J.J. Thomson received the Nobel Prize in 1906 for discovering that electrons are particles. However, his son George received a Nobel Prize in 1937 for proving that electrons are waves. Who was correct? They are both the answers. This concept, known as wave-particle duality, forms the foundation of quantum physics. It holds true for both electrons and light. At times, it is more advantageous to visualize light as photons, which are tiny particles, rather than as an electromagnetic wave. In addition to focusing light from far-off stars, a telescope serves as a massive light bucket to gather photons. It also implies that when photons strike an object, light can apply pressure. According to Rusty Schweickart, chairman of the B612 Foundation, we already utilize this to propel spacecraft with solar sails, and it would be conceivable to use it to divert a dangerous asteroid off course and prevent a collision with Earth. Number 8. Objects can be in two places at once. Wave-particle duality is one example of a superposition. That is, a quantum object that exists simultaneously in several states. For example, an electron is simultaneously here and there. It doesn't settle into one or the other until we do an experiment to see where it is. This means that probabilities are fundamental to quantum physics. Only when we look can we determine which state an object is most likely to be in. These chances are represented by a mathematical construct called the wave function. An observation causes the wave function to collapse, shattering the superposition and causing the object to exist in only one of its numerous potential states. The renowned Schrödinger's cat thought experiment is based on this concept. In an enclosed box, a quantum gadget determines a cat's fate. The device exists in both states until we take a measurement, leaving the cat in a state of both life and death. Number 7. It stops dead stars collapsing. The Copenhagen interpretation of quantum physics holds that observation collapses the wave function and induces a quantum choice. It isn't the exclusive choice available, though. The many worlds interpretation's proponents contend that there is absolutely no choice. Rather, reality splits into two versions at the precise time of measurement. One where we experience outcome A and another where we witness outcome B occur. It avoids the difficult problem of requiring an observer to trigger events. Does a dog or a robot qualify as observers? Rather, from the perspective of a quantum particle, there exists a singular, extremely strange world composed of numerous intertwined layers. As we zoom out to the larger scales we encounter on a daily basis, these layers unravel into the worlds of the multiple worlds theory. This phenomenon is known as decoherence in physics. Number 6. It helps us characterize stars. Stars' spectra can provide information about the components they contain, as well as their age and other properties. Niels Bohr, a Danish physicist, demonstrated that electron orbits within atoms also undergo quantization. They are available in preset quantities known as energy levels. When an electron releases a photon with energy equal to the gap size, it descends from a higher energy level to a lower energy level. On the other hand, an electron has the ability to absorb light and utilize its energy to accelerate itself to a higher energy level. This is a commonly used effect by astronomers. When we divide the light of stars into a spectrum like a rainbow, we can detect missing colors, allowing us to determine their composition. The energy level spacings of distinct chemical elements allow us to determine the composition of the sun and other stars based on the specific colors that are missing. Number 5. Without it, the sun wouldn't shine. You'll just have to trust us when we say that this is an image of quantum tunneling. Nuclear fusion is the process that produces the sun's energy. It entails the adhesion of two positively charged atom constituents known as protons. However, they repel one another, much like a magnet's two north poles do due to their similar charges. This is known as the Coulomb barrier in physics, and it functions as a wall between the two protons. Protons are particles that simply smash surfaces and disperse. No sunshine, no fusion. However, when you think of them as waves, the situation changes. When the wave's crest comes into contact with the wall the leading edge has already passed through. The proton is most likely to be at the wave's highest point. Therefore, it is occasionally present even though it is unlikely to be the leading edge. Fusion occurs as if the proton has smashed through the barrier. This phenomenon is known as quantum tunneling in physics. Number 4. It stops dead stars collapsing. Theoretically, when white dwarfs get older, their cores could crystallize. When the sun's fusion process ends, our star will eventually perish. The sun will eventually collapse due to gravity, but not forever. As it gets smaller, it packs more material into itself. Eventually, the Pauli exclusion principle, a quantum physics rule, comes into play. This principle prohibits the coexistence of certain particle types, such as electrons in the same quantum state. Astronomers refer to the resistance that gravity faces when it attempts to accomplish this as degeneracy pressure. A new object the size of Earth, called a white dwarf, arises after the collapse ends. However, the resistance to degeneracy pressure is limited. When a white dwarf reaches a mass comparable to 1.4 suns, a wave of fusion blasts it to pieces. This explosion is known to astronomers as a Type A supernova, and it has enough brightness to outshine a whole galaxy. Number 3. It causes black holes to evaporate. Certain materials do not vanish when they fall into a black hole. Some manage to escape. The Heisenberg uncertainty principle, a quantum law, states that two system attributes cannot be precisely known at the same time. The less precisely you know one, the more accurately you know the other. This holds true for location and momentum, but not for energy or time. It is comparable to taking out a loan. You got the option of taking out a large short-term loan or a small long-term loan. As a result, we get virtual particles. When we borrow a sufficient amount of energy from the natural world, we can create two particles that quickly vanish to avoid defaulting on the loan. This process was envisioned by Stephen Hawking to take place near the edge of a black hole when one particle escapes as Hawking radiation and the other is ingested. Since the black hole doesn't return the entire amount borrowed, it gradually disappears over time. Number 2. It explains the universe's large-scale structure. The cosmos has been expanding for 13.8 billion years, starting as a singularity. The Big Bang is our best explanation of the universe's beginnings. However, the 1980s saw the incorporation of inflation and different hypotheses into the Big Bang. The universe expanded from being smaller than an atom to roughly the size of a grapefruit in the first trillionth of a second. That is an incredible 10 carat 78 times larger. A red blood cell inflated to the same extent would be greater than the current observable cosmos. Since the newborn cosmos was initially smaller than an atom, quantum fluctuations associated with the Heisenberg uncertainty principle would have dominated it. The universe expanded quickly due to inflation before these variations had a chance to disappear. Astronomers believe that this focused energy into some regions rather than others served as seeds for material to assemble around to form the clusters of galaxies that we see today. Number 1. It is more than a little spooky. Quantum entanglement allows particles to be teleported or change their attributes. In addition to contributing to the demonstration of the quantum nature of light, Einstein promoted an additional phenomenon he called spooky action at distance. Even though we now know that quantum entanglement exists, we still don't fully comprehend how it works. Let's assume that bringing two particles together irreversibly entangles their quantum states. State A belongs to one, while state B belongs to the other. They cannot both be in the same state, according to the Pauli exclusion principle. The other immediately adjusts to balance out whatever modifications we make to one. This phenomenon persists even when we separate the two particles and place them on opposite sides of the universe. It appears as though information regarding the modification we've made has moved between them more quickly than light, defying Einstein's theory of impossibility. I appreciate you looking. Remember to subscribe and like our YouTube channel.